Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on Journal Physics 1, we want to start to talk about heat, work, as well as the first law of thermodynamics. So before we get started, if you want more of these kinds of videos, please consider subscribing as well as liking the videos, and also please check the description below for the notes that I have for this for this discussion. So let's just go into the topic straight away. So we want to first define what's the first law of thermodynamics, which is one of the important things that you always use in thermodynamics, which is the internal energy doesn't depend on the process. So last time we have already talked about that if you have a object with a certain temperature, it corresponds to a certain internal energy. So energy only depends on temperature, not the process. So for example, for the process, it could be if you apply some more energy through adding more pressure or heating the object up. It doesn't matter how you do it, but the only thing that matters is that it has this certain amount of temperature. So we know that the change in energy should also correspond to the conservation of energy as well. So if I have an object here with a certain energy and I apply much more energy towards the system, it will later increase its internal energy. Or also it could also just take something out as well. But taking the total itself, you could have work from outside and Q from outside becomes a work towards the outside and heat towards the outside. So the best way for me to actually to write this down is this is basically the change in internal energy is the work plus the heat going in. So there are lots of different books which basically discuss that something should go positive, some stuff should go to negative. But in here, I will try to focus on how much energy is added towards the system. So if you add work, so that means you apply much more work towards the object, that means its internal energy will go up. And same thing for the heat. If you apply much more energy towards the system, it will later increase. So that's the definition that I will use throughout this Journal Physics 1 topic. So here is something interesting for you to actually notice, is that you need to separate between two different kinds of variables. One of them is a state variable, while the other is a... No, sorry. Uh, I will just focus on the state variables. So state variables only corresponds to, to certain states, or states correspond to the variable. So one of the examples of this is for example potential energy. Another one is also internal energy, if you can see here, because it only depends on its state, which one of them is temperature. But some stuff, such as heat or even work, they depend on the process. So these are not state variables. So this is something interesting, is that if you add these two process variables up, you would get a state variable, no matter what it is. And this is interesting as well as a very useful tool for us to understand a thermodynamic system. So another way for us to write this formula is the change in the internal energy over time is the change of Q over change of time plus the change of work over the change of time. So this is sometimes the thing that we use. So so it is going to be useful for us to also discuss about this if you talk about small changes in time. So another thing that I will actually give out straight away is that you will have something called a PV diagram. This is basically a plot in which you get the pressure as well as the volume, and there will be some form of a system, for example, something like that, which basically corresponds to a certain kind of process that you are doing. And I will later discuss about how do you get the work, how do you get the heat from this plot itself. So to get started on this, we will start to discuss some thermodynamic processes. Thermodynamic process. So, so the way that you do thermodynamics is that you will assume a quasi-static process. Why is that? Well, later this will later correspond to something which you call as entropy, but for now we won't fully discuss about this because it might be much more harder for you to solve these problems, as well as the system will later become much more much more dynamic. That means that certain temperature between different between different places might be different. So instead we just assume the entire object itself is always within a equilibrium. So this is one of the ideas. This is always equilibrium. So if you do very small changes, it is as if that it will later go to equilibrium faster, so therefore you could just assume that it is always within equilibrium as long as you do the entire system very slowly. And this small process basically corresponds to a reversible process. So this means that you could actually turn it back on itself. So if the system goes something in this direction here, you can see here, that means that it could also go in the opposite direction as well, as long as it does it very slowly. But instead, there will be some work put in instead of put out and those kinds of stuff. But this only works for very slow processes. And and a irreversible process is basically when the process itself is fast or sudden. So we have already talked about this. So now let's actually talk about work itself. So we will try to prove what the definition of work itself is. So remember, work is basically the force times the ds, right? So instead, we will just assume a cylinder, something like that, and you apply a certain force here. And this guy has a certain area and a certain height. So basically, it has a volume. So now I will just push this a little bit down, which we'll call as the ds here. So just by looking at this, uh, you could write the change in the volume. The small change in volume will correspond to a ds, the negative of that. You could just see it from the diagram itself that the volume will decrease by ds amount, multiply that by the area. So that's the change in the volume. And so you could write this as f times dv, the negative, over a. And f over a in here, you can see that it's always normal. Therefore, you could state that this is negative p over delta v. Well, yeah, technically it should be delta v or delta s. And this is the work. So if you do this for when delta V goes to 0, you could write this as the dW equals to the negative P dV. So doing the integral itself, you would get the work to be equal to negative the integral of P dV. So that's the definition of work, as long as you assume that the work is going in the system. So the basically the outside world is giving work towards our system instead of the other way around. Because if it is in the other way around, that means the volume should go up. So that's the logic. So now let's start to talk about certain processes, which I will go and do a very deep derivation within each. So let's go and do that. So there's the isothermal process. So basically a isothermal process is where the T is constant. So basically iso is basically same, thermal is temperature. So that means the temperature itself should be constant. So if you actually look at this, and you would have a system which doesn't let out any gases out. Therefore, you could state that the amount of molecules should remain the same. So by using the ideal gas law, this is constant, and this is also constant, you would obtain this to also be a constant, which I will call as big C. So now, with this, you could write the P equals to C over V, right? And so trying to figure out what the integral is for the work. Oh yeah, by the way, if you actually plot this on a PV diagram, this would correspond to a process something like that. You could see that this is the P, this is the V, so this guy corresponds to this guy. So increasing the temperature basically means that you actually increase its furtherness from the center. So now, after we figure out the relation between P and V, we could actually start to figure out what the work is, which is the negative integral of the constant, which you could bring out, dV over V. And you would notice this to be the negative C, natural log of Vf minus Vi. And so basically, for a process, you would always have a initial condition here as well as the final condition. And this is for the volume itself. So you would figure out this to be the negative. And here the C is the nRT, right? And all of these are constant anyways, with the natural log of V final over V initial. So that's the relation of a isothermal process. So in the notes I write it as V2 over V1. Well, in here I will write this as the final over initial. So there might be some things that might be different, but I hope that this doesn't truly changes the full meaning of it. So you could see that the work itself, as long as the V is greater, that means that the object itself gives out work, which makes sense. So looking at the heat, we need to know this fact from last time. The Q is the E minus work. And if you actually notice about this, the energy itself doesn't truly change. Oh, sorry, this should be the change of everything. Technically, all of them is a change in internal energy, change in heat, as well as the change in work. Technically, it's something like that. So basically, this change of heat is always zero because you don't change temperature. So therefore, you just need to figure out what's the negative work itself, which is here, and RT natural log of the V final over V initial. So that's for the isothermal process. So let's actually start to think about a new kind of process, which is the constant volume, which sometimes you call this to be isometric or isochoric or isovolumic. So something for you to notice for a isochoric, one is that the V is constant. And therefore, you would notice that the work itself will be zero. So basically, if you have the PV diagram here, the V is constant, that means it goes something like this. It doesn't even have a area. And here's something that I haven't really mentioned. Basically, the PV diagram tells you what's the work only by looking at the area between your process as well as your V axis or the volume axis. That's basically the definition of work. So going back, you would get this. And here's something that I want to bring up is that if you actually remember, the Q, the heat itself is like mc delta T. This is something that I will try to bring up, is that if you actually increase the energy of, so if you try to increase the internal energy of a system, it goes mc delta T. And actually you could actually change this in such a way that you could write this as m over n multiplied by nc delta T. No, sorry, yeah, something like this. So now I will just combine this m over n, which is sometimes you call it as the molar mass, and you multiply it by the heat capacity, by the specific heat capacity. And therefore, you would get something called the CV, or basically this is the molar specific heat for a constant volume, because we're doing this at a constant volume. So we get this as well to be NCV delta T, because work plus Q should be the energy, which is NCV delta T. So that's just it. You don't even need to do much of the computations. You know that the internal energy itself will be NCV delta T. And here's something for you to remember. Energy, the internal energy of a system is a state variable. That means no matter in what method that I go, the only thing that matters for the change in internal energy is its change in temperature, which is always NCV delta T. Well, CV could depend on the material, but the formula itself doesn't truly change. So that's something for you to remember. So now when we start to talk about the isobaric, or basically pressure is constant, you would know one thing. Work should be negative PV, because if you do the integral, it's the integral of dV. So this is basically V final minus V initial. So that's just it. So what about its heat? What about its internal energy? This might be a challenging thing for you to figure out, but this is a very cool fact for you to know. So if you actually rewrite this, energy should be Q plus V, right? Q plus work. So something that you figure out is that so this is negative P delta V. So this would mean P delta V should equals to Q minus N Okay, and CV delta T. And from last time, the Q should be, so the CP should be, so this guy would also have another formula, right? From here, so basically, every single time if you do a certain process, there is always a specific heat or the molar specific heat that corresponds to that process. So in here, we could call this as the CP delta T because we assume that the change would be only depending on the pressure. But for the internal energy, it is still CV because it is a state variable. It doesn't matter how I get there, I know that it should be the same. So we got this relation. So now looking at this again, you could actually rewrite this as, so P delta V itself can be written as NR delta T. So you would get NR delta T, which equals to N delta T Cp minus Cv, right? So here's a fact for you to know. You could cross out all of these to get the R to be equal to the Cp minus Cv. So for any kind of, so for any ideal gas, because remember we are doing assumptions with ideal gas, you would get the specific molar heat, molar specific heat for constant pressure minus the one for volume would always equal to the ideal gas constant. So that's an interesting fact for you to remember. And so you could write, so you would get the work to be the negative PD delta V, and for your Q, it's NCP delta T, which basically is the same thing as NCV delta T plus P delta V. So that's an interesting fact for you to remember. So the last one that I want to discuss is about the adiabatic process. So for a adiabatic process, basically the Q would be 0. So there's always certain kinds of system in which you could have its Q to be 0. So one of those is if you have this object inside a, let's say like a thermos, and you can basically increase the pressure or decrease the pressure inside of this thing as long as there's no heat going out or in towards the system. Oh yeah, by the way, this one here, the graph is something like that. So this one might be much more challenging for you to figure out what the formula is, but I will do this anyways. So you would know that the work itself should be NCV delta T dt, and the work you would know this to be negative P dV. So now let's actually convert some stuff first. First, you would know pressure PV equals to nRT, right? From the ideal gas law. So you would get negative nRT dV over V, which equals to NCV dt. So one of the ways for you to solve this differential equation basically is to just to separate its variables. So you would get, so the n could cross each other out, and you would get the negative RT dV over V equals to, let's see, CV dt over T, right? There. So now, let's actually go ahead and integrate both sides. So you would get negative R natural log V final over V initial, which equals to CV natural log of the T final over T initial. So now with this, okay. So maybe this might be a little bit challenging for you to solve now, but here's a way for you to actually to rewrite this. You could state that the CV, natural log of T, plus R, natural log of V, would be a constant. Why is that? Because if you actually try to separate them both, you could just rewrite them as CV natural log TF plus R natural log of VF, which will also equal to the initial. And this works for any different kind of points. So that means that it should always remain constant. So that's an interesting fact. So now, with this, you could just rewrite this into T to the power of CV plus, no, sorry, multiply that by V to the power of R, right? Which is a constant. And so now, let's actually go ahead and take all of this to the power of 1 over CV. So you would get TVR, which is CP minus CV over CV, which is a constant. So you would get TV equals to, that's negative 1, and CP over CV is something that I will define now to be gamma. So it's gamma minus 1. So now looking at this, let's actually rewrite this in a much more friendly way. So PV equals to nRT, right? Let's just substitute this again. And later the nr could be brought to the right hand side. So you would get PV to the power of gamma is a constant. And this is the condition for a adiabatic process. You would always have PV to the power of gamma. So your graph will be a much more steeper version of the isothermal. So for example, if this is the adiabatic, this is the isothermal. So that's basically one of the conditions for a adiabatic process. And remember when we did wave motion, one of them was the speed of sound itself, which we figure out that it is gamma p over rho. This is what the gamma truly is. It is the ratio between the molar specific heat for constant pressure over constant volume. But I won't fully derive how you get that velocity now. So I will just leave it up to you for you to figure that out on your own. So now with this, you could just always state that your energy is basically the work, which equals to the negative integral PdV, right? So plugging this in, you would get the negative of, so dV over V to the power of gamma. This would equal to negative, so it's V to the power negative gamma. It's 1 minus that over 1 minus gamma with a constant there. So this will be, so the bottom one will be gamma minus 1. And then we just plug in, we are just plugging in the V to the power of gamma again. But we will just use for the specific version. So for example, if this is V final, that means we will use P final. So it's P final minus P initial over, oh wait, sorry. Yeah, P final, V final minus PI, VI. So basically you could see this to be some form of like NR delta T over gamma minus 1. Well, actually this is correct. So I didn't truly write it in the in the in the formula itself, but you could use this to actually to figure out what's your work done. You could just use this formula as well. So that's a adiabatic process. So now I want to bring up this new question, which is, what about if you have this entire process, but you actually do it from point to point? Well, it is still simple. You just need to break it down and then just do the corresponding processes. For example, if you know that during one step it's a isothermal, you could just use the isothermal formulas. And then after that it's adiabatic and whatsoever. And one of these process is a cyclic process known as the Carnot cycle, which goes something like this. So this is isothermal, and then this is adiabatic, and adiabatic. So I believe it goes something like this. Yep, it goes something like that. And this basically generates work as you supply heat in. And something for you to remember is that if it goes back to its origin, that means that you convert all of your Q into work or vice versa. So here I supply Q in, and as well there's some Q out. The delta Q here corresponds to the delta work. So you could just compute that on your own. So now I want to talk a little bit about the specific heat for gas. Specific heat for gas. And something that I will just bring up is the CV itself. So the CV for a monatomic gas, monatomic gas. So basically these are points. So you can just assume the gas to be certain particles, something like that. It has 3/2R. And basically, this here is like something like helium, xenon, radon, what else? Neon, argon, those kinds of gases in which they don't really pair with other kinds of particles. So this is related to certain chemistries. And so there is also a diatomic gas. So this is if it has two particles. So this means that it is 5/2R. So it's something like that, and then it has a bond. So it always comes in pairs. Something like O2, N2, F2, and more of these diatomic gases. So how do people manage to figure out what each of these R's truly is? Well, you figure it out using the equipartition theorem. So this basically means that the average energy per degree of freedom is 1/2 kT. This is for one particle. So if you have a mole of particles, this would be half RT. So this is the part in which we compute. So for a monoatomic gas, you would have degree of freedom going in this direction, as in that direction. So it's 3/2R. But you could have a particle, something like this. This is a diatomic. It can move between the directions, as well as it can rotate within this direction, as well as in this direction. So there's 5/2Rs. And then sometimes you could go all the way to 7/2R. And this corresponds to a diatomic particle, but if you apply high temperature. So this will later gonna also introduce vibration as well. So something goes like that, or something that goes in and out. So there is 7 over 2 R's in this case. And this truly depends on your particle itself. So something interesting to actually realize is that for a diatomic particle, if you do it within low temperatures, you could get it in a way such that the the CV itself is 3 over 2R, or it could go towards 7 over 2R. But it doesn't have a place in which it is 2R or 3R. It can only be between 2 over 2, 5 over 2, or 7 over 2. And why is that? So this actually goes into the idea of quantum physics, in which for rotation to exist, it must to be within a certain energy band. So for something to vibrate, it requires a certain energy band, in which some of these doesn't have. So that's something interesting to also keep in mind, is that there are certain things that you cannot truly explain by classical physics. So at the future, I will later discuss more about quantum physics as well as modern physics. But for now, I will just leave it here and wrap up this video. So thank you very much for watching this video, and I hope that this video truly helps you to understand more about thermodynamics as well as the first law. And so with that, if you want more of these videos, please consider subscribing as well as liking, and also don't forget to share this video with others that needs it as well. So thank you very much, and I will see you on the next video.